Welcome to this session on farm brand mechanisms, where we're going to do an introduction and give you some quick examples so that you can learn how you can be able to use brand mechanisms in your own projects with a great profit. So we're going to see why they are needed, what they are, and their applications. Brand mechanisms are needed simply so that you can be able to build affordable large-scale robots. And the brand mechanism was actually designed for that particular purpose, for building an affordable large-scale agricultural robots. They have the advantage of the precision of fixed robots and as well the range of mobile robots. Combining this into one requires a brand mechanism or any other means that we still do not know about, but brand mechanism will do pretty great on that. If you need to reduce the cost of building robots, and if you need double precision of fixed robots. So let's consider, for example, these two cases where you have FarmBot, agricultural robot, and Tetel, weeding robot. Tetel is nearly a weeding robot, not an agricultural robot. Tetel, the robot itself goes for $349 and it can work an area of 18 meters squared, but it has several accessories that almost double its price. And then we have FarmBot, cheapest, which can work just 2.97 square meters. But how much does it cost? $1,700 for 3 meters, 1, 2, 3 length and 1 width. The most expensive working 18 square meters is $5,000. Brand mechanism needs to bring a cheap robot. Some trade-offs that you have is precision. We will see this thing about precision because we say we need the precision of mobile robots, but we have to make some trade-offs there. What are brand mechanisms? Simply defined, a class of mechanisms for turning fixed robots into compound robots. The main requirement for a mechanism to be a brand mechanism is that it has to have two parts, a mobile robot part and a fixed robot part, having independent movements, independent control of their position. The mobile robot part of brand mechanisms have discrete position, while normal mobile robots have continuous position. So brand mechanism robot, the mobile part, you tell it, come from 0 to the next position, which may be 1 meter, but it's not continuous. Well, it goes through that continuous motion just so that it gets to the intended location. Then the position of the payload of brand mechanism is only partially dependent on the position of the mobile robot part. This is captured in point 2. Now let's get to the interesting part where we have examples and implementation. So we will give you 3 examples. One is uses a non-circular wheel to achieve intermittent motion. One uses a back flipping frame, and one has 4 legs, 2 on one side, 2 on one side of set. And then there's the last one, the most practical, the one that is actually being used to build robots at the moment, uses a chain. So allow me how to go and share with you this. So we're saying the first one is a non-circular wheel and then a back flipping frame. So here, right here, if you can see, is a wheel, but it is not a continuous wheel. It is not a circular wheel, because you could just put a box around it and you can have as many of these points. Now we have 1, 2, 3, 4 points. You can have as many of them as possible, as long as they are not enough to form a complete wheel. So here's the motion. we're saying there's a fixed robot part in black, and then the rest forms what is a mobile robot part. So we're seeing the motion of the black does not really depend on the motion of the other part. So those motions are independent. So fixed robot moves, and then it gets its position. Intermittent motion, it stays at the same position. Then the mobile robot comes forward. Fixed robot stays at the same position. Mobile robot comes forward again, and it continues and continues. The issue that you will have with this is that the payload is being raised up and down. It's not a very efficient mechanism when you use that non-square wheel. And then there's a back flipping frame. So again, black is the fixed robot. The rest forms the mobile robot. So if we are to see its movement, then we see how it moves. There are two frames that form the mobile robot, and they carry the fixed robot. So fixed robot moves, and the mobile robot backflips, so that there can be continuous motion of the fixed robot. I'm going to increase speed of this so we can see it going back as well. And then the third one, which is we do not have a model and simulation for, is the two, we're saying 4 legs of set one from the other. We do not have an illustration for that at the moment, but what we have is what is practically being used, and what we have is practically being used, and it is a patented design. What you have, which is working here, it is just so I think I may have skipped something. So here's a concept of what we'll do with brand mechanism. Now, trying to reduce the cost. So if we had a fixed robot moving on some rail, for example, an aluminum extrusion, how would we reduce that cost? We can try saving the material. What does that do? It removes the excess material that we do not need, and yet we have to have our calculations right so that we don't interfere with the structural integrity. So if you had the whole material, it is clear that in most cases, we don't really need all of that, so we can remove some and we have it this way. But now you see, if we do this, we will have our fixed robot here being supported, not being very stable, because of sometimes it's only supported by 2 legs, if we call them legs, the green, 1 and 2 legs. But we can also try something to increase its stability. So you're seeing we have offset the other legs by half of the distance between 2 successive legs, so that at any one point it is being supported by 3 legs. So we have the 3, and then the next 3, etc. and etc. And then, interesting, this is the concept that you have in what you're saying, the 4 legs of set is the 4 legs of set. It should be showing us something, but if we remove the rail, so that it's not a rail, so now it's just a robot. So we have this leg here, and this is another leg. As the robot moves forward, this leg moves from this position to the next position, so that by the time the robot gets there, that leg is in that position. As it continues moving, once it has passed this leg that is here, this leg should be carried from here to the next position. So we have a walker, but one that we're able to achieve with much greater precision. And then this is now the last example that we're giving, a practical example. And this is actually the model of a robot. Let's make it walk so that we see how it works as we make it walk back and forth. Much slower, Mr. Robot. So there, but clearly you can see that there are points that it will not be able to be supported. Like at this point, I believe it's only 2 legs down. It will not have sufficient stability. So we can increase the number of sets of legs. Each set has 3 legs. So the first set on each side, 1, 2, and 3. First set on each side. So if you put it 2 sets, then you have how many? That's 6, 1, 2, 3, 4, 5, and 6. Then you can make it work, and you see that at any point there are at least 4 legs supporting it, and that will give it sufficient stability. And for simplicity, that is what we prefer, but you can go on and on and on and on as many legs as you want. But then this robot can also turn into a brand mechanism. So when you want it to go fast, you let it just walk around like that, or move around like that, or roll around like that. However, that motion may be called as a normal mobile robot will do. But then you can turn it into a brand mechanism. Then you notice again, if we reduce the speed, that the yellow bar would form for us the fixed robot, and then the rest of it forms the mobile robot. So again, no relation. The range of the mobile robot is pretty much increased. It's as though we had one long rail from this end up to the other end. So the yellow or the fixed robot is for us moving. And what is the difference between this and our normal robot? Primarily, there are 2. It is much more easy for us to position the brand mechanism. On the other side, you are much easier for us to know when there's sleep or any other thing than it is for us to know about this. And then again, we can achieve very high precision with the brand mechanism. We have a design that uses a lead screw, another one that uses a tooth belt. So we can achieve the precision of a lead screw with that. So with those examples, we can try to see what it is that let's get to the uses of the brand mechanism. Currently, we know of one use. We are the ones that are using it in designing what is going to be the world's cheapest agricultural robot. Thank you for tuning in.